Well, so mathematics has different topics, and under those topics there is what we call all subsections. Under those subsections there is what we call numerical methods. So in numerical methods we look at different things. There is what we call linear interpolation and extrapolation. There is what we call numerical integration or trapezium rule. There is what we call errors. We have location of real roots, where we talk about the NRM, the general iterative formula, the linear interpolation and extrapolation, and finally we have what you call the flowcharts. So in today's lesson we want to discuss a topic under numerical methods, which we refer to as numerical integration. Now just like pure mathematics, in pure math we look at integration, and we say that an integral is an elongated s. For example, this symbol here is referred to as an integral because it is an elongated s. But then if it is pure math, we always generate what we call exact values. All those methods of integrations which we discuss in pure, they give us exact values. Now in applied math, we make use of the area of the trapeziums which we studied in O level, and we apply it in the applied math. And it is from the area of a trapezium that we can calculate the area of any given curve. So if you want to determine the area bounded by this curve and the x-axis from the x-coordinate x is equal to a up to x is equal to b, then in applied math you will be using we shall be using trapezium rule to get the value of this integral. But then if it is pure, you integrate using those specific methods and you generate an exact value. So if it is pure, we use an equal sign, and if it is applied, we use an approximate symbol. So that is why you're seeing here approximately equal to. Approximately equal to mean that we are getting an approximate value of the area covered by this curve and the x-axis from here, which is x is equal to a, up to here, which is x is equal to a b. Now because we deal with the real numbers in applied, we are going to assume our first x value is x naught, so we are calling it x naught. When x is a, it is x naught, so they keep on increasing until when you reach the very last value, which we refer to as xn. So x naught is the lower limit of the integral, and xn is the upper limit of the integral. So whenever you get any of these x values and you substitute them in the function of x, which we are referring to as a y function, y is a function of x. So whenever you get an x value and substitute it here, you get the corresponding y value, implying that if we get x naught and we put it here, we are going to get y naught. If you get x1 and substitute it here, you will get y1. The same applies to x2, x3, xn, and also xn minus 1. Now according to the flow of our x values, they are dictating how the y values must also be written or expressed. So if it is the x1, the x value before becomes x naught. If it is x2, the x value before becomes x1. If it is x3, the the x value before is x2, and if it is xn, the x value before becomes xn minus 1. So if this is xn minus 1, then the x value before here would be xn minus a 2. So you keep on subtracting a 1 on the subscripts to get the corresponding x values. Similarly, when you go to the y values, if this is y1, the y value before becomes y0. If this is y2, the y value before becomes y1, and so on until when you get to the very last y value. So why call it the trapezium rule? After drawing the curve, we just create these middle lines so that we can have the trapeziums being written there or being extracted there. So if this is the first line and this is the second line, we can generate a trapezium from here to here to here to there. We can generate another trapezium from here to here to here to there. So A1, A2, A3, and so on up to AN, they represent areas of different trapeziums. A1 is the area of the trapezium which runs from x0 to x1 to here to there. A2 is the area of the second trapezium which runs from here to here to here up to there. So it is the essence of calling it the trapezium rule. Now, just like other graphs in math, if you want to generate the scale that you are supposed to use along the x-axis, there must always be consistency in the values that you put on the x-axis. So that brings us to what we call the h. H, now in this case, it is going to stand for the smaller change in the x values. That if you are on x0 and you want to go to x1, we are going to get x0 plus h and we get x1. x1 plus h and we get x2. x2 plus h and we get x3. xn minus 1 plus h, we get xn. What does that imply? If you want to get this smaller change in x, we get the last x value minus the first x value divided by the number of spaces in between the x values. We have 1, 2, 3, and so on up to the nth space. We call them sub-intervals or strips. So if you want to get the value of h, you say h is equal to b, where b is the upper limit of the integral provided, minus a, where a is the lower limit of the integral provided, divided by n, where that n that we are talking about must be number of sub-intervals. What do we refer to as sub-intervals? They are these spaces in between the y values. That if I have 1, 2 y values, then how many spaces are between 1, 2 y values? It is only one space. So it is one sub-interval. If there are 1, 2, 3 y values, how many spaces are between there? There is 1 and 2. So there are 2 sub-intervals. So we get the last value, the upper limit of the integral, minus the lower limit of the integral, and we divide by the number of sub-intervals that we are intending to use. So every after an x value, there is a smaller h. If you pick any two consecutive x values and you take their difference, you must get this value of h. So that h is b minus a over smaller n. So from here up to there it is h. From here to there it is h. From here to there it is h. From there up to there it is h. So the essence of drawing this is to help us derive what we call the trapezium rule. So how does the trapezium rule operate, or how is it derived? Like we have said, if you want to generate the area of any given curve, you create various trapeziums and you find their area. So we have created our trapeziums. There is this up to the last one. Now we are going to get the area of the first trapezium, which is A1, the area of the second trapezium, which is A2, the area of the third trapezium, which is A3, and so on until when we get to the area of the last trapezium, which we are referring to as the AN. Now we are extracting a trapezium at a time, and we read off all the values that correspond to it. The first trapezium runs from here to here, but from here to here it is H. Then it has from here up to here, which is Y0, and from here up to there, which is Y1. So this is what we call A1. Now A2, this is now A2. So we have A2, A3, then AN. So this is our A2. A2 is this one. It runs from here up to here, but from here up to there it is H. From here to there it is Y1. From here up to there it is Y2. So that is the structure of the second trapezium. The third trapezium is this. It runs from here up to there, so it has Y2. From here up to there it has Y3. From here up to there it has H. Then and so on until when you get to the very last one that has Yn minus 1 and Yn, then H. So just like we saw in O level, the area of any given trapezium is given by a half H into A plus B. So our A is this. All these ones are values of A's. All these ones are values of B's. So for the first trapezium, which is area 1, we are going to have a half H into A, which A is now Y0, plus B, which B is now Y1. So it is a half H into Y0 plus Y1. Then you go for this, a half H into Y1 plus Y2. Then you go for this, it is a half H into Y2 plus Y3. Then you go for the very last one. You don't forget to include these because they tell us that we are supposed to continue with as many trapeziums as possible until when we get to the very last one. So our last one is also a half H into Yn minus 1 plus Yn. Now what do you realize about A1, A2, A3 and AN? They are all having a half H, a half H, a half H, a half H. So we pull it out. After pulling out a half H, then amongst these Y values, there are Y values which are repeating themselves and some other Y values which are not repeating themselves. So when you look at this formula, this is Y0 plus Y1, but then in the second formula we have Y1 plus Y2. So you are seeing that Y1 is composed in A2. You realize that Y2 is going to be composed in A3. The same applies to Y3. It will be composed in A4. Then Y4 will be composed in A5. Then this Yn minus 1 is composed in some other area before this one. But Yn and Y0, they are not composed in any other areas except this and this. So we are picking Y0, put it here, and Yn, put it here, because these two are not repetitive. Then all the others are repeating themselves only twice. So that is the essence of putting here A2 and all other Y values from Y1 up to Yn minus 1, implying we have only excluded Y0 and Yn because they are at the extremes of our curve. So they are not repeating themselves here. So our trapezium rule will then be, if you want to use trapezium rule to get the value of the integral from A up to B of any given function, say this, then it is given by a half H into Y0 plus Yn plus 2 into Y1 plus Y2 plus Y3 and so on up to Yn. This is Yn minus a 1, up to Yn minus a 1, and it is what we refer to as the trapezium rule. So in our next series, we are now going to see how do we then use the trapezium rule to get the value of any given integral in applied math. Thank you for listening.